recording.
Enough that we're going to see Happy Garbage Day?
Oh, yeah, you know what, you're right, except that I still get really warm. So yeah, the merch will make an appearance at some point. But this afternoon, I'm actually giving a talk online to the University of California, Davis's quant group, and so I thought maybe that would not be the day to get out the merch. So I'm trying to do like the professor gear, at least, on camera. I do have shoes on, so that's my concession to being in person. But hello, everybody. Welcome back. So I have some good news for you. For those of you who've already finished formative assessment number 4 that's due on Monday on Halloween and thought, I really wish that Lisa would put up another homework so that I didn't have to work on my thesis or this paper or this writing that I don't want to do, you're welcome. Homework 4 is available. And do you know how I know that? Because I put up your homework instead of doing the writing I was supposed to do yesterday. So this comes from a place of understanding. But as I was working on it, I realized that we haven't gotten far enough into the ordinal items to be able to have it due when I had intended on the 7th, so I bumped it to the 14th. The good news is that there are, of the 4 sections, you can do sections 1 through 3 right now. It's only the 4th one that we haven't gotten to. So you can take your time going through it, fitting it into your workload as you're available to do, and then the revision to homework 3 will be due the same day, but that's optional. And you can't work on that yet, so the other homework is the last thing that you have. So just wanted to alert you to that change in the schedule, so nothing is due on the 7th now. So any questions on that? Logistics stuff? Good on that? All right, I'm going to shut this down then. So what we have left is a little bit of lecture 5 and example 5 to cover how one does model comparisons when we are using a different method of estimation. So what's the new set of letters that we talked about last time? If we're not using ML, what are we using instead? That one. WLSMV, which is weighted least squares with a mean and variance correction, otherwise known as diagonally weighted least squares. So WLSMV is an M+ specific thing, but diagonally weighted is the broader term for it. And the big picture that goes with that is literally a picture. The idea of tetrachoric correlation. So limited information is starting with an estimated tetrachoric correlation matrix for a series of binary items, and then estimating all of the factor model parameters that would best try to recreate that as the answer key. So it's more directly analogous to what we had in CFA when we had the right answer as the saturated model. So the H1 model is the data estimated tetrachoric correlations, where each of these is the correlation that would be most consistent with the division of responses into these 4 quadrants under a bivariate normal distribution. So if the items were perfectly correlated, we would expect all of the people to be either in cell A or D, and this would look like a line. To the extent that they're not perfectly correlated, we would have some people get one answer right that didn't get the other answer right, and vice versa, and that would then create these 2 off cells and a correlation that's less than 1. So we're starting with a summary of the data and then estimating the model on that summary. Now, why would we do that?
Absolute model fit?
Absolute model fit's a big one, because now we can, if we have the answer key, if we have the saturated model, what do we get with it then? How about a significance test? Get one of those for whether the model fits? Yeah. It's not exactly a likelihood ratio test, but it's in the same family. What other fit indices are relative to perfect? More letters.
Ramsey? RMSE?
RMSEA, yes, root mean square error or something or another. Yeah. SRMR, yeah. I think those are the 2 main ones besides the model test.
Can we get that?
What?
The last one?
SRMR?
Yeah.
Yeah.
Good.
Yeah,
Okay.
so the SRMR is how far off on average each of the correlations is in the data versus the model, where the data is now the tetrachoric version. And if we can make a tetrachoric correlation matrix, we can certainly make a null model version which gives us CFI, TLI as well. So yeah, the idea that we can easily test model fit is one reason to switch to limited information. What about rectangling? Remember that? Quadrature? Trying on 15 different types of genes in each dimension? That whole thing? Yes, we don't have to do that if we're in limited information. So for models that have a lot of different latent factors in them, WLSMV is going to be quick and relatively accurate. Now you don't get something for nothing. What's the downside?
DSK, Probit?
It's in probits. Yeah, we'll call that a downside. Yeah, we have to switch to a different link function, but we can rescale it into logits if we wanted to. It was a question you asked me before. Do you remember? No. Okay. Missing data. Yeah, what about it? It's going to mess things up. That is correct. Yes. Any more details than that? No? Okay. Yeah, would you like to throw it to someone else? What kind of missing data are we assuming if we start with a summary that doesn't know how the summary was created? Completely random. Yeah, so the acronym is MCAR, missing completely at random, and that is exactly what it sounds like. That the data that you're missing has nothing to do with what it should have been or any other information about the person. That's a pretty strict assumption. In contrast, anything involving maximum likelihood, full information approaches where you're starting with all the original data and not a summary, full information is missing at random instead, which sounds like it would be the same, but it's not. It's conditionally random. It means that after I know what the answers were to the rest of your questions, and after I know these characteristics about you, then I can say that it's random conditioning on those things. And that you can't test, so you can't ever know if it's good enough. But it's a more reasonable assumption than completely at random. So that's the downside. So if you're in a situation where you have a lot of latent factors, you want to test model fit in a direct and straightforward way, but you're worried about missing data, that's where you might have to do like a two-stage multiple imputation to address the missing data plus estimation using WLSMV. Or switch to Bayes, and that's Wednesday, Friday class instead. So that's not my territory, but something for nothing. You don't get everything you want in one fell swoop, but I think that's true in most things of life. So the one thing then that we have left to talk about is in this version of it. So full information, we get our log likelihood, we get AIC and BIC. When we switch to WLSMV, scrolling through all the stuff here, the output looks like this. We get a chi-square test of the model fit, so our predicted factor model relative to the perfect model, but we don't get any log likelihood values. So this will be your first clue that you can't do a likelihood ratio test if you don't have likelihoods. We're missing the information. But the way that we will do it is something called diff test. And this is an approach that you cannot do by hand unless you're willing to do some calculus. No thank you on that one. And as near as I can tell, it is not directly programmed into Lavaan either, which is why on your next homework I'm asking you to use M+, because that's the only way I can guarantee that you're going to get the right answers. I tried it in ANOVA in Lavaan, and I got the right integers, but not the right decimals. So I think it could work well enough, but I'm not 100% on that, and so that's why I'm not going to recommend it. But to do model comparisons, the rule is you start with the model that has more parameters, then you estimate the model that has fewer parameters as the comparison, and it has to be in that order or it will yell at you. So for example, these are the data that we were playing with last week and I think the week before. 7 items, yes or no answers as to whether each older adult in this study could do various activities of daily living. So the differences in terms of the code, this part right here, so under the analysis option, we've switched from estimator equals ML to estimator equals WLSMV. The next one is a scaling choice parameterization, that's a mouthful, equals theta, that gives us the probit scaling. So this is directly analogous to what we would call an ogive model, where we're pretending that the underlying continuous variable for each of the binary responses has a variance of 1. So the error variance in the model is fixed to 1 for identification. So that's one switch. And then here is one other new thing. The save data option. There is a command, it's called difftest with 2 F's, one word, and it wants the name of a data file. It needs to be a .dat extension, but what you call it is up to you. So I've named my data file 2p because I'm going to be comparing it to a 1-parameter version as the nested model. So this is going to save all of the information to a separate file when you estimate this model that then you will refer to in estimating the nested model. It will go grab that file, read the information, do the calculus, and spit out the results for you. So the two models being compared, I have called them 2p and 1p for 2-parameter versus 1-parameter, and we previously called them 2pl and 1pl, right? Why can't I have the L anymore?
The scale is different.
The scale is different. L stood for logistic in logits. Now I'm in probits. So I could do 2pp and 1pp, but I don't think that's a thing. And exactly, people are going to start giggling if I say pp too much, and so we're not going to go there. It's just 2p and 1p. So for those of you who had M+ yell at you that you had over 255 characters, yes, I know, I'm sorry. I don't know why it doesn't happen to everyone. It only happens to some people and only on some models, and I have yet to figure out why. But this is another instance in which you may need to put the full path to the file, just like you had to do for the data. It's still better than paying $800 for the software package, though. Am I right? Yeah. Okay. Well, then
No, I agree.
pay your $800, and yeah, it's fine. It's an expensive package because I think it's worth it. All right. So then this side, the rest of the model, looks very much the same as what we had before. The only difference is that rather than referring to intercepts, we refer to thresholds, $sign. So if you forget the $sign and you try to make this an intercept, it will yell at you. And I always think of the $sign as a mnemonic that if I ever want to get paid, I need to know what a threshold is, because someone will always pay you to learn this so that they don't have to. So $1 means item 1's first threshold. Given that these are binary items, there is only one threshold. ... until lecture 6, in which case we're going to have more than one. I have written for completeness, but you don't have to write that the error variances are all fixed to 1. That will happen automatically, but I try to be transparent in terms of what parameters are being estimated versus fixed. And I have identified the model by fixing the latent factor variance to 1 and the mean to 0, as we usually do. Okay, any questions thus far? Today I learned that expired Mountain Dew tastes remarkably similar to unexpired Mountain Dew. So, pro tip for you. All right, so here's my model. I believe we looked at this last time, but here's a warning message that I usually don't bother to print that I did, just to remind you. It's like, hey, you can't do difference testing in the usual way when you use these estimators. You need to use difftest, so it's trying to do you a favor and help you out. So what do we think about this model? Not bad. RMSEA is a little iffy. We'd like it to be below 0.06. The test of close fit is, ironically, very close to fitting closely. Not quite, though. CFI and TLI are happy. They are happy differently because they're based on a different standard, right? Null model. How much better is this model than the worst possible model? It's quite good, actually. And SR-MR, same thing. How far off on average is the correlation between what the model says and what the data say? Off by 0.04 in a correlation metric, that's pretty good. I'll take it. So then the comparison model will find the differences in the code. What's different on this side? There should be 3 things relative to the previous side. First, let's look at the model part. What's different on the right-hand side for the model syntax? And Zoomers, you can play along too. Any ideas?
Loading word constraint.
Yep, this word right here. So by labeling 7 parameters, 7 loadings with 1 word, I'm doing what to them? Making them equal. Now, why would I do that? This is a model that has a special name. It's a Roche model. So if reviewer 3 says, you should have fit a Roche model to this, you can say, I tested that, and it was garbage. Yeah, probably.
Sorry.
Yeah, no, I heard that, and I agree. For these kinds of items, right, where the items are different things, it seems unrealistic that they would have the same factor loading. For other kinds of items, that might be a more plausible belief, but it is ultimately a testable hypothesis. What you type in here can be anything that you want. So if you look at the M+ documentation, they usually are pretty lazy. Like they'll put like a 2 in here. And you're just supposed to know what that means, like what 2 means. So, I mean, you can type anything you want, right? Like, this is the stupid model. I can put that as my label. It doesn't care. The only thing it will care about is that it has 8 characters or fewer. So I tend to put things in here to remind myself what I'm doing, trail the breadcrumbs, as it were. So I'm constraining all of the loadings equal. And what am I asking then? What research question would merit me actually doing this? What do I want to know?
Equal discrimination.
Equal discrimination. So are all the items equally related to the latent trait? Are they all equally good at their respective difficulty levels is the question. So now how do I get the model comparison? I take the same data file that I saved and I move that reference to it under analysis instead. So I run the model that has more parameters, save that piece of output to a physical file. Then when I run the model that has fewer parameters, I refer to that saved file, it reads it in and does the difference testing for me. So it should have the same name in both places, just under save data when you're initially running the model, and then to refer back to it, it goes under analysis instead. In the results then, I have 2 different chi-square tests that will show up. The first one is the test of absolute model fit. So relative to the perfect model, where perfect is defined by the data estimated tetrachoric correlations, how much worse is mine? What do you think? Chi-square of 64 on 20 degrees of freedom and a p-value that's 0 to 4 decimal places. Yeah, it's worse than perfect. Now here's the one that I'm more interested in. Chi-square test for difference testing. That is what it's labeled, by the way. So this is the model comparison.
Using
Diff
the
test. Yep.
Yep.
Yep, it does it for you. So there's no more typing things into spreadsheets or having to run extra pieces. It does it for you. And if this doesn't show up, watch for an error message that says your models are not nested. What it probably means is either they're not nested or you got them in the wrong order. The one that has more parameters always has to come first, and the one that has fewer comes second. So we start with the 2 parameter, then the 1 parameter. So this degrees of freedom for that model comparison is 6. Why 6?
Because there are 6. Like if we let them be unique, there would be 6 additional.
Exactly. I'm going from a model that had 7 loadings to a model where I only have 1 for a savings of 6 parameters. So the chi-square for difference testing, the comparison of those 2 models is a test statistic of about 17.8 and a conventionally significant result. So I could talk about this from 2 different perspectives. I could either say the Roche model fits significantly worse, or the 2p model fits significantly better. Dear Reviewer 3, we tested the Roche model. It did not fit as well, so we did not include it. This result is now reported in footnote 39. So the conclusion that we would draw that these items are not equally discriminating is the same regardless of whether we're using limited information estimation or whether we're using full information. We came to the same conclusion. Everything else is exactly the same in terms of definitions, concepts, and whatnot as to what the model parameters mean. The only catch is that we're in probits. Do you remember what a probit is? Z-scores. So under the standard normal distribution, it is the z-score that goes with the area under the curve to the left. So that's what is being predicted as the y. So for instance, the factor loading for item 1 here, for every unit higher factor score, so given my scaling of theta with a standard deviation of 1, I'm talking about a standard deviation difference in factor, the probit of item 1 response goes up by 2.7.
I'm sorry, can you say that one more time?
Yes. So for every 1 unit change in the factor as the predictor, which means 1 standard deviation higher, the probit of item 1's response goes up by 2.6.
Thank you.
Yep. So it is a linear slope if the y-axis is probits. It becomes the bendy slope if the y-axis is probability. Now here's the downside, which I think you said one of the bummers is probits. How do I take this prediction that this is creating and back translate it into probability? I can't do e to the model over 1 plus e to the model anymore because I have to do integration instead. So you'd have to look up what the p-value is that goes with the predicted z-score or find it in a table somewhere. So that makes it a little bit trickier to go back down to probability, but still not impossible. And our best friend thresholds, same thing as before. This is telling you about the average person and what their expected probit is of answering a 0. So thresholds mean difficulty. Higher thresholds means a more difficult item means you're more likely to have a 0 than a 1. We get the standardized model results the same as before, except they're standardized using a different variance, a variance of 1 rather than 3.29 as we had in Logit's. And then M+ helpfully gives you the difficulty discrimination version of the same parameters. So the difficulties are then the new piece of information. The loadings and discriminations are exactly the same. And difficulties then, cough, cough, quiz question. What's the difference between a difficulty and a threshold?
The location of 0.
Where the 0 is, right? Yeah. So what are you going to say?
Difficulty and threshold?
Mm-hmm.
Oh, well, sorry. I was thinking threshold and intercept.
Oh, yeah, threshold and intercept. What's the difference between them?
The location of 0.
-1 for threshold and intercept, right?
Yeah.
Now if we get to difficulties, how do we get from an intercept to a difficulty? Or a threshold to a difficulty? They're both locations. Do you want to see the picture? Would that help? Maybe? I think pictures generally help. Plus, I just really like this picture, so. This one. Slide 63. So thresholds and intercepts tell us about the average person. If your theta is 0, here's your logit of the probability of a 1. Here's your logit of the probability of a 0. If you're in limited information, okay, here's the probit of the probability of a 0. Here's the probit of a probability of a 1, where the 0 is given by the threshold. The 1 is given by the intercept. But rather than talking about what is predicted for the average person, B says, how much theta do you need to get to a response of 0 in logits or probits? So B, difficulty, is what is the theta value at which this curve crosses 50-50 in probability? So B does not talk about the average person. B talks about how much theta you need to have a 50-50 shot. To me, much more useful. But both B and intercepts here are essentially different locations on this x-axis, which is why I think of them both as location parameters. It's just that B is more useful because it tells you how much data you need to have a good chance at this item. So difficulties are here, thresholds are here. And if you don't like thresholds and you're like, can I just have an intercept? Yes, you can. Watch carefully. Ta-da! Now it's an intercept. And the other last piece of this, local fit. Do you remember local fit in CFA? Looking at the discrepancy matrices. So they were in covariances, correlations, and then normalized and standardized versions of those. Now they only come in one flavor. They only come in correlation flavor, but this is what that residual option gives us. So this is the difference in the model predicted correlation relative to the data estimated correlation, and they're in correlation metric. So I've highlighted the ones that look to be relatively big, like the correlation between 1 and 7 is off by a correlation of 0.1, and it's negative, which tells us what?
Less correlated.
Yeah, they want to, the model thinks they're more correlated than they are. They want to be further away from each other. So that one and that one are the only things that look like they could potentially be problems. Given how small the discrepancy is in correlation metric, and given that I don't have any reason to think that these items should be differentially unrelated, I'm going to call it good. So if I were to look at the cheat codes, technical term for cheat codes, what are they called for real? Mod indices, modification indices, yeah. They would probably say, hey, I can fix this for you. I think you should estimate a residual covariance between 3 and 5. Now here's the fun part. In WLSMV, you can do that. You can't do that in ML. So let me show you what that would look like. Slide 88. We've almost made it to the end of this slide deck. I know, right? It's exciting. So when you are estimating factor models for categorical data more broadly, in full information maximum likelihood, error variances for the items are not parameters. That means you can't ask for an error covariance between two items either. So you have a lot fewer options potentially to remedy misfit that way. You would have to somehow introduce an additional relationship between two items using a factor instead. So I wanted to show you what that would look like so that you have a full menu of choices here. Let me make this big for a second. So error covariances in WLSMV are estimated and written about in exactly the same way as CFA. So for instance, if I had 5 items on that are supposed to be measuring one trait, but then I have some reason, either theoretical, empirical, or hopefully both, to say that item 2 and 3 want to be more together than what the factor predicts, I just write the error covariance just like this. So this works as it should in CFA. It works as it should in WLSMV, limited information estimation. It does not work in full information. But here's how you trick it. You make a factor instead. So this is heading into something that's known as a bifactor model in the IRT literature more broadly. It would also be considered a method factor in the CFA literature. We will talk about those in greater detail in Unit 8. But just for now, to show you how the trick works, if you have these two items that want to be extra together, you can define a new latent factor, and I've named it error fact for error factor. I've fixed both of their loadings to 1, and then I've estimated the factor's variance. And that factor variance then creates an additional relationship between items 2 and 3 that is separate from and incremental to the relationship that the factor itself originally predicted. The critical thing here is that the two factors have to be unrelated or this blows up. So if you want to introduce residual correlation type parameters and you're in full information estimation, you have to do it this way as its own factor. Now I fixed both of these factor loadings onto this new residual factor to 1. Could I have estimated them instead? Could I have estimated both of them? Think back to identification. How many items do I need to define a factor? I need 3. So the fact that these are constrained equal is because there's only 2. So if I am trying to estimate a positive residual covariance, I would fix these two loadings to 1. If I wanted to estimate a negative covariance, then I fix one of these to -1 instead.
Wait,
Wait,
was
what?
the negative one? Sorry,
So,
I wasn't following that.
no, so if I want to introduce a positive error covariance,
Okay.
the way to do that through a factor instead is to fix both of the loadings to +1. If the error covariance that I had wanted was going to be negative, then I have to change the sign of one of these loadings and fix one to -1 and one to 1.
Why would we want negative error covariances? Sorry.
Why would we? Because sometimes that's what the data want, like right here.
So, okay.
So what that would essentially do is take the predicted correlation between the two given by the factor and lower it. It's like you're subtracting
Adding,
from it.
Almost like suppressing it or something.
Yeah, you're like reducing their relationship by saying, no, they don't want to be that together. Okay, fine, I'm going to estimate their errors and let their errors go against each other, and the net result then is a lower correlation than you had before. So in this example, for instance, if I wanted to remedy these two sources of relative misfit, I could make up a new factor that would have a loading of 1 and -1 for these two items, and I could do the same thing for these two items. Or since we're in WLSMV, I can just do the width as a direct error covariance.
Do you have a path diagram for this second factor?
Um,
Or is it essentially like factor all of the things?
I do.
Factor and it's like a cross. I just want to confirm that visually I'm thinking of this.
Yep, and now I'm thinking that would have been a good picture to put in here. But, you know, one would think that 90 slides is sufficiently comprehensive, and one would be incorrect on that point. No, I was literally just thinking that. Like, I have a picture, I just need to find it. I know what I'm looking for. It's in Lecture 4. Here it is. It's this picture right there.
Yep, that's what I was thinking.
Yep.
Awesome. Thank you.
Do you remember this? In CFA, if you have two items that want to have an additional relationship, here are equivalent ways of making that happen. You can let them have their own factor and let that factor be correlated. You could let them have an error covariance, and that's cool as long as you're in WLSMV, but it is not an option in ML. Or you could do it this way, which is to allow the additional relationship through a separate uncorrelated factor that each items load equally onto. So this version right here, this additional factor that just captures that extra part is called a bifactor, or a specific factor, or a method factor. But the reason why bifactor models are talked about in IRT is because you don't have the other choices available to you if you're doing full information maximum likelihood. You have to do it this way.
What slide is that again in lecture 4?
This is slide 69 in lecture 4. Yes. And this is from your textbook, by the way. Page 181 is where I stole these pictures from. All right, does that help?
Thank you.
Okay. So just sort of to put a pin in this, like as you are working towards homework 5, so those of you, how many of you had to add error covariances to make your model fit in homework 3? Okay, I would have expected more, but quite a few folks. So if you wanted to do that in homework 5, you'd have to do it this way. But that one's not up yet, so we'll get there. All right, 237. How we doing? All right, Zoomers, how you doing? Can I see some thumbs? You know, or poop emojis, whatever you want to send me. That's our thumbs down symbol, it's poop emoji. Oh, they're all up, thank goodness. All right, yeah. So then here's just an example of what that would look like, where you get the variance of the error factor, and that becomes, takes the place of the residual covariance. There we go, we made it. Hooray. So just as I had for example 4, there are lots and lots of words here at the end of example 5 that you can use as a starting point to describe your own analyses for homework 5 if you're using binary data. I will have a separate version of this for example 6, which is what we're doing next. And that's that. Okay, I think I hit everything finally. Any questions? Feeling good about this? Feel like you can do this if you need to? Maybe with a little bit of scaffolding? All right. Then I have some good news for you. Most of you have ordinal data instead of binary data, right? There are no new concepts to get ordinal data instead of binary. You already know everything you need to know. There's only one catch. We have to take our ordinal set of responses and we have to make binary items out of them. That's what's going to happen. It does it for you, but that's the idea of how we move from binary to ordinal. We're going to chop it up into a series of binary items. So we're starting then lecture 6. And since we're starting a new one,